If you have watched my other videos, you now know how to calculate Nash equilibrium and how to find which strategy would be preferred by which player. But is that universal? Do we always have a Nash equilibrium for every kind of a game? Let's look at a particular example of a game where we do not have the normal kind of a Nash equilibrium which we were discussing so far. Let's look at this game where we have two players, A and B. A is our row player and B is our column player. So if A is to choose between top and bottom when B is taking left, he would definitely take bottom because 9 is greater than 5. So I will put a star over here. And if he has to choose between top and bottom when B is choosing right or R, then definitely he will choose 7 or top, as 7 is greater than 3. What about player B or the column player? When column player has to choose between left and right or L and R, if the row player is choosing top, he will definitely take left because 9 is greater than 3. And similarly, if he has to choose between L and R, when row player is taking B, he will take 10 or R because 10 is greater than 2. And as you can see over here, there is no cell in this payoff matrix where you have double star. And when you do not have a double star in any payoff matrix, how can you conclude that we have a Nash equilibrium? So in this particular game, we do not have the kind of Nash equilibrium we were discussing. Now, what exactly is the kind of Nash equilibrium we were discussing? If you recall, player A, player B over here are choosing just one strategy at a time, either top or bottom or left or right. But John Nash gave a very important idea, or rather he proved the existence of something called a mixed strategy Nash equilibrium. Now what exactly is a mixed strategy? When you interact with someone, do you always interact in a particular way? I mean, let's suppose you are playing cricket or baseball or hockey or football, or you're just trying to talk to your friend. Do you always behave in a pretty standard, predictable kind of a way? No. There are things which you do with probabilities. If I think it in a mathematical way or a game theoretic way, you have fixed actions which you do but with certain probabilities. At times you might be angry with your friend with the same input given by that friend. So your response to any event in your normal life, be with a friend or in a game, depends on a lot of factors and is not always decided by just one factor, which is what the other person is doing or what you can look at as of now. So in mixed strategy, what we have is probabilities on actions or probabilities on strategies. So in this example, what we could have is that player A is choosing 30% time top and 70% time bottom, and similarly player B could have taken 40% time left and 60% time right. Now you can change these probabilities, and there could come a situation where a probability combination of player A and a probability combination of player B gives you a kind of Nash equilibrium which is known as mixed strategy Nash equilibrium. And John Nash proved that this happens always, but only with few caveats, which are for our level that the game should be finite in nature, the number of players should be finite, the number of actions or strategies possible for each of the players should be finite. Now let's look at few notations so that we understand what exactly is a mixed strategy and how do we go from there to mixed strategy Nash equilibrium. This was our usual notation for pure strategy games. N is the set of players. So I belongs to N, which means if you have 3 players, N is 1, 2, 3. So I belongs to 1, 2, 3. Now if you're 2 players, N is 1, 2. So I belongs to 1, 2. Now if you have player I, for player I, capital SI is the set of pure strategies, or rather pure strategy set for I is capital SI. Now what is utility for player I? For player I, utility is a mapping from the product set of strategies to real number line. Now what do I mean by product set of strategies? Product set of strategies mean that I take all the strategy sets. Let's say you have 2 players. So S1, capital S1 into capital S2. That is your product set. So capital S1 into capital S2 to real number line. Now if you have a bit of understanding of set and relations, then you would have automatically understood it. But I have already discussed this in the previous videos, so you should go back to one of the previous videos of game theory, the first 2 videos, and have a look at how do we get utility from strategies. So this was all about pure strategy. Now what about mixed strategy? For mixed strategy, we do not have capital SI, but what we do have is delta over capital SI. This can also be referred as capital MI, just for the sake of easy algebra. So we have capital SI for pure strategy games and delta over capital SI or capital MI for mixed strategy games. Now what exactly is delta over SI? Delta over SI, as we've already covered in the first part of our video, is the motivation behind probabilistic strategy, that I'm giving probabilities to all my pure strategies. So if my SI was a set containing 3 actions, I'll give probabilities to all those 3 actions, and if SI has 2 actions, I'll give probabilities to those 2 actions. Now those 2 probabilities can take any number between 0 and 1. So there is a lot of possibilities, or rather a lot of different combinations possible over here. So if we take all such combinations of probabilities, 0.2, 0.8, 0.3, 0.7 and so on, and make a set, that set will be a capital MI. So don't think of it in terms of set, but think in terms of possibility. So all possible probabilities for a particular player over his pure strategies is your set of mixed strategy or capital MI or delta over SI. And how do we get the utility for mixed strategy games? We just replace capital SI with capital MI, because earlier we had to choose over capital SI, now we are choosing over capital MI. So if we take all the probability combinations for all the players, that set to real number line mapping is known as the utility for player I. So I'll rephrase that. A mapping from the product set of probabilities to real number line is the utility for player I. So this is my mixed strategy utility for player I. Just to expand on this definition of utility, we can also write utility for player I in this form. If we take all the probability combinations, then definitely if we want to calculate utility, we need to take one such probability combination for all such players, which is small m. If you recall this, for the pure strategy case, even there we were doing the same. We used to take one small s, which was the combination of strategy choices by all the players. So this small m is the combination of the probability choices by all the players. So this gives you the utility. Now what exactly is this? This is sum over all my pure strategies, and I am calculating what is my product of probabilities over here. This m is product of probabilities of all the players for that particular strategy combination into the utility for player I for that particular set of strategy combination. Now I will just detail you what exactly is MS, and then you'll understand what I'm trying to explain. So what we are doing over here in small ms is product of the probabilities for all players, given that I have to choose this strategy set small s which belongs to capital S. So this small s could be something like S1 dot 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 Sn. So I have to calculate utility based on the probability I am giving to S1 and so on till Sn for all players from 1 to n. So if I know the probabilities, I multiply them because I'm assuming that all the players are choosing independently. So I can multiply independent probabilities. So this will give me the probability for this particular strategy combination, small s. So if I have small s with this probability, multiply this probability with the utility of that strategy combination, and if I sum it over all such small s which belongs to capital S, I'll get the utility for player I, given he is part of a game which is played with this set of probabilities small m over my pure strategies of capital SI. So I hope this was clear to you. If it is not clear, just try to put a numerical example on top of it and you'll understand this idea. Keep watching this video so that you understand it further, because I am trying to give you a postgraduate course in quantitative economics in this video format. So a few things over here could be a bit extra for your understanding, so bear with it for me. Let's just take the example of prisoner's dilemma, where you have player 1 choosing confess with a probability of 0.3 and not confess with a probability of 0.7, and player 2 is choosing confess with a probability of 0.4 and not confess with a probability of 0.6. Now, if we want to calculate utility for player 1 or 2, what we need to multiply over here is the product of probabilities. So let's say I want to find the utility for player 1 given that I have confess not confess. Then definitely I look up my payoff matrix and find a utility from here. Now if I know the payoff matrix, I can find out all such combinations utilities for player 1. Now I can also do one more thing. I can also find the probability of landing to this particular cell CNC. So probability of this happening is 0.3 into 0.6. So I'll multiply this thing with 0.3 into 0.6. Now I will do the similar sort of thing for not confess, 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 and not confess, not confess, and calculate these values for all the other three possible choices which we have. Now if we sum it over, then we will get the utility for player 1 when this is our probability choice by both the players. So this particular thing over here is your small m, and now when we sum this thing over, we will get utility for player I when we have this m. So I'm not spoon feeding you these calculations because I want you to work through this, as I have given you everything which is sufficient to understand the calculation for mixed strategy utilities. Now let's just move to the idea what John Nash gave us, how John Nash expressed his proof that there exists a mixed strategy Nash equilibrium always. So let's just head over to that algebra. Let's take a very simplified algebraic form of a game. You have two players, 1, 2, and both of them have the same strategy set S1, S2, which is AB. So utility for any possible combination over AB, which is A, A, AB, BA, BB is easily calculatable if you have a payoff matrix or if I just give you these values. So this is pretty standard. After this, here comes the idea of mixed strategy calculations. I need to calculate utility for both the players U1 and U2 over all probability combinations possible, all small m possible. So what do I mean by this is my M can take any possible probability combinations over AB. So how I can represent this? Let's just say player 1 is choosing A with a probability of P and player 2 is choosing A with a probability of Q. This is player 1 and this is player 2. So automatically they are choosing B with a probability of 1 minus P, and over here this is 1 minus Q. So if we know how they are choosing A, we definitely know the probability of their choice of B. So I can represent this small m with simply small p comma Q. This would suffice to represent this particular choice of probabilities, because this thing over here is your small m, but we do not need to write all of this, as PQ is summarizing this behavior. So if we have PQ, what do we know? What can we say? Rather not us, but what exactly is John Nash saying over this game if we are changing PQ and trying to find whether we have a mixed strategy Nash equilibrium or not? We can interpret John Nash's existence theorem in this particular framework with this algebra, that there exists a set of probabilities P star Q star such that utility for player 1 in that combination of probabilities P star Q star is not less than the utility for player 1 if he changes that probability from P star to any P which is permissible. And also for player 2, he can also not improve his utility by changing his probability from Q star to any Q that is permissible. Now in these two inequalities, the key idea here is they are trying to deviate unilaterally. Again, the same principle of Nash equilibrium. There is no profitable unilateral deviation. And in this particular framework, when you have only two players and they have only two pure strategies, there exists a P star Q star such that there is a mixed strategy Nash equilibrium. And if you go into more detail of it, pure strategy Nash equilibrium is a kind of mixed strategy Nash equilibrium where the probability is given all to one strategy and the other strategies are given zero probabilities. So I hope you understood the idea of mixed strategy Nash equilibrium, and you would also remember after this video that there exists a mixed strategy Nash equilibrium even if there is no pure strategy Nash equilibrium in that particular game. With this, the video comes to an end and I would meet you again in another video. Till then, bye bye. And before you go, why don't you subscribe if you haven't already, and also press the bell icon.